Okay, welcome to lecture 10, I think this is, and we are going to change subject completely. So today we start on a new topic. And it's an extraordinarily difficult topic for many reasons. In certain sense, it's an unfinished topic. If you have good ideas, you can finish this topic. It is an idea of how to calculate things or how to define quantum theory, but all aspects of it are not rigorously understood, so it's still under research. But in the meanwhile, since we physicists are practical people, we keep using it, and it's very useful. So we'll have to study it in a spirit of a practical spirit. And in fact, what I'll do now is to show you the motivation, how we arrive at a path integral. But please don't confuse that motivation with a derivation. You can't actually, at least up to now, we don't know how to derive the path integral approach. Okay? It's an alternate approach to quantum theory. Any quantum theory can be quantum mechanics, can be quantum field theory, can be relativistic, non-relativistic, that doesn't matter. But it's an alternative approach from the canonical approach where things are there are operators and states. In path integral, we don't have to bring in operators and states. We have to do something different, but we are supposed to get the same answers. So why are we trying to introduce a new approach if it's supposed to give the same answers? Well, in some problems, this approach could be easier or it could be more difficult than the other approach. The calculational steps are not at all the same. In fact, they look very different. Sometimes we know how to get the answers only in the path integral approach, and we still don't know how to get those answers in the canonical quantization approach. And this is especially true for field theory. In particular, any non-perturbative physics in quantum field theory is generally approached by this method, including studies of gravity and quantum gravity, okay, but especially gauge theory. Well, especially all of them, but gauge theory is the one which has yielded very concrete results, and gravity has yielded also many results. So you can study semi-classical gravity, as I'll explain. And so the motivation is that it's like a new formula. New, of course, new means before I was born, forget about you. So it's new compared with the old formulation of quantum theory. No canonical quantization. And the things which go with canonical quantization, like operators, so Hilbert space, operators, states. Now this is too strong a statement. Of course there is a Hilbert space and of course there are operators and states. It's just that in the calculation we don't encounter them. We have to interpret the answers in these languages. So we don't work with non-commuting quantities, and therefore obviously we don't have canonical quantization, which is the statement that position and momentum don't commute. That thing is not the way we do path integrals. So in that way it's quite radical and new. Okay. In fact, in some sense it only uses an infinite dimensional integral over classical fields. So in path integral language, classical fields are important, and we get rid of the complication of all these operators and states, but we take on a different complication of having to do an infinite dimensional integral, which is not much fun. If you have tried to do a three-dimensional integral, most of the time we don't even know how to do that. So how are we going to do infinite dimensional? Well, we have to be creative, and actually we don't know the general answer. We have to sort of make up some consistent answer as we go along. Okay. So these are the features. One more feature, which is quite amusing, is that in non-relativistic quantum mechanics, it's actually more complicated. That is to say, there are simple problems which can be done by canonical method, and which you have already done and which you already know the answer, and we can reproduce those calculations in path integral by doing more work. So it's very depressing. It's like, why are we doing more work? But in relativistic QFT, strangely, it appears less complicated. And in fact, as I just said, you can do things by the path integral method which you can't even really figure out how to do practically in the canonical approach. Nobody is saying that in principle it can't be done in both approaches. If both approaches describe quantum theory, then everything should be doable in both approaches. And the best thing to keep in your mind is, well, both approaches are available. We'll use one or we'll use the other as we find convenient. I've mentioned this philosophy many times, that in the more difficult your theoretical framework like QFT, the more you have to rely on multiple approaches and make a wise judgment which one is good for you. But you can't do that till you learn how path integral works, so that's what we are going to do. So now we are going to actually go through something which may look to you like a derivation, and up to some point it will be a derivation, and then at the very last step, a hole will open in the ground and we will fall into it. So then the derivation will sort of fail. But we would have reached the path integral, and at that point we have to think and use our ingenuity. So let's start with a quantity which I hope you have encountered in non-relativistic quantum mechanics. Not only it's non-relativistic, but it's for a particle moving in one dimension. And what we do is we start the particle in a position eigenstate with position xi at time ti, and we allow it to propagate freely or with some potential, that's up to us. And at time tf, it should have reached the point xf, and we ask what is the amplitude for this propagation. And as you know, if I take the mod squared of such an amplitude, then I get a probability for propagation from one point to another, which is a calculable thing in quantum mechanics. Since it's non-relativistic, there are no fields, there's no gauge invariance, there are no special symmetries, there's nothing to fix. So it should be quite straightforward. This goes by the name of the propagator. And by definition, it is, so often these formulae start from the right hand side. We start with the state xi, position eigenstate xi at time ti. Then we evolve it using the Hamiltonian. And now I'll put a hat on things which are operators, because soon we are going to lose these, but while we are using operators, let's put a hat to make sure that we know it's an operator, and this is the Hamiltonian, of course. And then times Tf minus Ti upon h bar. As you surely know, this is the unitary operator which, given a state like this, evolves it for a time difference Tf minus Ti. So since it starts at Ti, it will end up at Tf. And when the state has been evolved for that much time, then I ask the question, what is the amplitude for it to be found at the point xf? So therefore I take this state, I evolve it, and then I project onto that state, thereby taking the matrix element of this unitary operator, and this is exactly the propagation amplitude. No questions about this. It's not something that QM courses focus on, but they should. It doesn't require anything more than non-relativistic QM. It's much simpler than, say, hydrogen atom as a problem. You can put any simple Hamiltonian like p squared by 2m, which we are going to do very soon. So, okay. So this is a unitary operator sandwiched between position eigenstates. Okay. Now there's a property which is pretty obvious, which is supposing I take this propagator and start at xi ti and go up to some arbitrary point x bar and t bar, and then I multiply by the amplitude to start at x bar and t bar and end up at xf and tf. And I integrate over all possible, I can't stop my hand putting that arrow sign. Okay, integrate over all possible dx bar. So what is this physically? The amplitude for the particle to start at time ti, then I pick a time t bar which is between, so it's important, t bar should be between ti and tf. It's some intermediate time. I don't have to specify what it is. Then I say, well, I take the amplitude that the particle started at xi at the initial time and it reached a point x bar at time t bar. Then it started at that point and reached the final point, and I integrate over all possible intermediate points x bar. What should this be equal to? Same thing. Should be, right?
But then shouldn't there be a dt bar?
No, there should not. This is why you should think about it. In quantum physics, x is a function of t, right? Okay, so t is something which is, time is evolving. Okay, there's an initial time, there's a final time. Let's draw it. So let's imagine here is the initial time, here's the final time. Okay, now the particle starts at this time. Let's make it a space-time diagram for convenience. This is ti on this axis, and this is tf, and this is xi, and this is this point is xi, and this point is xf. Okay. Now the particle has to start, this is okay, I think. The particle has to start at this time, at this place, and it has to end here. Okay. How many paths are there between this and that? Possible paths? Any path? I didn't specify any rule what path I should take, so all possible paths. However, we should be a little bit careful. So for example, this is a path, this is another path, this is another path. Okay. Now here's another path. Is this allowed? What did think in your mind, what did the particle do in that path?
Cross the speed of light.
Speed of light. Where did the speed of light come in? First of all, we are doing non-relativistic physics, so speed of light is infinity. Can cross the speed of light, can't cross the speed of light, whatever it does. But if you really want to confine this to relativistic physics, you have to put everything in the forward light cone, and you can still do things like this. So good or bad? If my job is to start here and end there, then halfway through the process, I might go for a walk to the main building and come back there. Have I done anything wrong? I've not done anything wrong. We're all looking so disapproving and sad. This path is as good as this path, or this is certainly not the most optimal, but we never said it should be optimal. Okay, how about this path? This definitely can't happen. The path has to move monotonically in time, otherwise it isn't a path. This one has moved forward in time and then backward in time. Not at all the same thing. Not allowed. It's totally not allowed. So now let's look at our time t bar. This is a time t bar, randomly picked to lie in this interval. Would you agree that every path from here to here which is allowed intersects this dotted line at exactly once? Okay, so that's the proof of this formula. It intersects the dotted line at some point, this path. That point is x bar. This path intersects at a different x bar. This intersects at a different x bar. I sum over all the possible intersection points, x bar, and that's it. There's nothing to sum over t bar. I can pick t bar arbitrarily. There's no meaning in summing over t bar. I pick one t bar and I slice the whole space of paths into two halves, before t bar and after t bar, and then I integrate over all the ways they can pass through this dotted line. That's all paths. Now at this point, if you were fussy, I sense that you are not very fussy, you would say things like, can I allow a path which comes here and has a sharp kink like that and comes back? Should I have a smooth path? Should it be differentiable? Now you're asking sensible questions. Okay? And we'll defer any discussion of those questions. But this thing is a given in quantum physics, and we can just create position eigenstates, take the Hamiltonian and just do the calculation. We'll get an answer. So that's the definition. Okay? And it satisfies this convolution property. Okay. Now let's find out how we could compute this for a simple example. By the way, this property, because it is bilinear in U, it says that integral U times U is U. So it fixes the normalization of this thing once and for all. It can't be true if I multiply this by 5 or 10. Everything has to be correctly normalized for that to be true. In fact, there's a simple proof of that relation also, which is that I just break this exponential into the evolution over, anyway, let me not go in there. Let's not go into that just now. We are going to do that shortly. Let me first tell you how to calculate. So we first calculate it one way, just using our elementary knowledge of quantum mechanics, nothing fancy. What should we do? Well, experience teaches us that the Hamiltonian of any system usually has some energy eigenstates. If I know those energy eigenstates, then this thing is easy to calculate. How? Introduce. Thank you. Introduce was the correct word. Introduce complete sets of states. I think that's what you were trying to say. So here we will put a psi m, the ket of a energy eigenstate or stationary state, and then here we will put this operator. Please keep remembering that this is not h bar function of tf minus ti, but h hat times tf minus ti. It's h times t over h bar and then xi ti. Oh, sorry. Here also I want to introduce another set of complete set of states. And of course I sum over all m and n. So sum over m of this is 1 or identity operator, sum over n of this is identity operator, so I have done nothing. But now the matrix element I want is h between psi m and psi n. That's very good, because by definition h on psi m is em times psi m. So I've chosen these to be energy eigenstates. Can you think of some reason I didn't put a time argument here and here? The Hamiltonian we'll assume is independent of time, and therefore these are stationary states. So it doesn't, the time doesn't matter. They only evolve by a phase with time, but then the phase will cancel between these two parts, so it's perfectly okay. And so using this relation, we get summation xf tf. So what will happen? H will act on psi n and give me En times psi n. Now the overlap psi m psi n, if everybody is correctly normalized, is delta mn. So one of these sums will go away. We'll only have a sum over n, and we'll have here psi n, then here we'll have psi n xi ti, and we'll have e to the minus I En tf minus ti. One h bar is just a phase. That's a pure number, so I took it out. So everything is a pure number here. One number times another number times another number. And I perform the sum, and that's the answer. How well I can perform the sum depends on knowing these e's, which, since I didn't tell you what is the Hamiltonian yet, you can't do any more with it. But this is the in principle solution to the problem. Right? So far so good. It will work very well if you use a free particle or harmonic oscillator, anything quite simple. And if you use something more complicated, you may need to make some approximation and whatever. But anyway, we'll be calculating this soon for a few examples. But anyway, the main point is that what is this? This is the overlap of the stationary state with the position eigenstate. So in position basis, if you know the stationary state, then you already know this. This is nothing but the position basis energy eigenfunction. That's the definition of this. The overlap between the position eigenstate and the energy eigenstate is the thing which normally in quantum mechanics you call psi n of x and t. And likewise that one will be psi star n of xi and ti. So you have to know these in order to make any further progress. Good. So let's keep this fact in our mind and let's notice one thing. So this insertion of two complete sets of states is good way to calculate the quantity, but if we just want to recast it in various ways, nothing stops us inserting lots of stationary states anywhere we want. This is some time interval over which we are propagating. I can break it up into small intervals and keep inserting complete sets of states. Okay. So let's write. Let's notice that u of xf tf xi ti can also be written summation over a collection of integers ni, not integers, I mean there are some labels, xf tf psi n. I'll explain my notation in a second. It's always confusing to write these things from left to right. They become much more logical if we write them from right to left. I'm not very good at that. Then so I'll explain in a picture what I've done and it will become very clear. And the last entry is psi n1 e to the minus I h over h bar. Okay. So what I did was, I noticed that there's a time interval tf minus ti and I broke it up into capital N equal parts. Okay, in that picture which I drew for you, that dot, instead of that dotted line at time t bar, which was arbitrary, I put n dotted lines at times t1, t2, t3 up to tn, exactly at equally spaced intervals. I hope you can imagine that. And then what I did was, I took so this is the first one, this is the one that's already in that formula. Then instead of evolving this for the full time, I evolved it for 1/n of the time interval. Then I inserted a complete set, psi n1, and here there'll be a psi n1. Then, then again I evolved by that 1/n of the full time interval, then I inserted another one, and I went on until I insert the last one, and then of course I have my position eigenstate at the end. So I've done something which is not wrong. This is the formula, iterating the original formula. It says that u of xf tf xi ti is the product of u's of 1/n of the interval integrated over all the intermediate points. Okay, but not exactly. What I did was to integrate over the intermediate energies rather than points. So I inserted energy eigenstates. Okay. Okay. Now this step is has no advantage. It's just to show you that quantum mechanics allows us to insert complete set of states, which surely after going through 3 quantum mechanics courses, you know that very well. Okay. The interesting thing is that we can also, instead of doing this, we could insert position eigenstates instead of energy eigenstates. So wherever you see psi like this, I'll just put x. Then it will be more like what I did before, where I did this intermediate, this formula for the intermediate x bar. So let's write that formula. Remember that here to use completeness, I had to sum over all these indices n, from n0 to nn. But if I insert position eigenstates, then I have to integrate over the position. Even for energy eigenstates, I might have to integrate. I don't know the Hamiltonian. If it's continuous eigenvalues, then I will have to integrate over them. So it's just a symbolic notation. But now let me try to write the formula that I want in the same way, but with position eigenstates occurring everywhere. So what I'm going to do is keep these operators the same, and I'll only change these all the way to the beginning. So here, the last one, okay, I'll also change my notation little bit with your permission. The final one I'll call xn tn, and the first one I'll call x0 t0. It will make it much easier to write formulae. Okay, then here I put this thing, then here I put x1 t1, here I put x1 t1, and I repeat. So here I have x something. Let's say here I would have x. So this can act directly on x. Then here I will have xn minus 1, tn minus 1, and xn minus 1, tn minus 1. Okay, is it reasonable? Sorry for messing up the writing. I think you know what is going on here. So this is also allowed. I start with the original position at the original time. I let this evolve for 1/n of the full time interval. Then I put position eigenstate. Then again evolve, position eigenstates, evolve, and so on. And at the end, I need to be just a little careful. I should integrate over what? Can you tell me? x1, x2, x3 up to n minus 1. Beautiful. So everyone is with me. And not integrate over the initial and final endpoint because they are fixed. So this is actually in the same spirit as the formula we gave at the beginning. And so we have derived simple identity that this quantity, or now renaming this as x, I should have probably started with this. Is the same as integral dxa product over a from 1 to n minus 1 product of u xb tb xb minus 1 tb minus 1 from b equals 1 to n. It's a little tricky to get these endpoints right because u depends on 2 neighboring arguments while the measure depends only on 1 argument. You're supposed to integrate over all the intermediate arguments which are 1 to n minus 1. But when b is 1, this is 1, but this is x0, this is not integrated. And when we take the last one, when this is n, then this is xn tn, which is not integrated, so it's not in that. So there are n u's and n minus 1 integrals. Okay, good. Now we have generalized our original formula by including an arbitrary number of position eigenstates on the way. Before we do anything more, let's just make a picture of it, and let me just mention a little bit the history. So the picture now in the same diagram that I drew earlier has T0 here, Tn here, x0 here, xn here, and I have these dotted lines going all the way, and each of these is of size Tn minus T0 upon n. In fact, I'll simplify it, I'll call it T by n, where T is equal to Tn minus T0. In fact, I'll even simplify it further. I'll just call T0 as 0. This is my choice. Okay, now what you see is, I'm saying, okay, I have a path from here, which at T1, which is this point, lands somewhere on this path. We don't know how. But once it is here, then of course it would continue and land somewhere on this dotted line, and then it would continue and land on this dotted line, and so on. Okay, and once I sum over all possible places it can hit this dotted line and this and this and this, then I've got back all my original paths. Good. So up to now, we haven't done anything except restate a formula for a very standard quantity in terms of more complicated quantities, but it's basically the same quantity. So it's like an iteration of one quantity. So nobody can argue with it. And now comes the miraculous step. So first let's think, what is this telling us up to here? It's telling us this wonderful probabilistic property of quantum physics, that a particle is basically trying to go from here and end up here. This is its end point at time Tn. And quantum physics tells us very clearly that it can do whatever it likes, go wherever it likes, as long as it ends up there. Okay? And this slicing makes it very explicit, because the original thing was just a amplitude to go from here to here, but now we have broken it into sub-amplitudes to go from here to here, here to here, here to here, but we see that where it lands on the dotted line is entirely up to the particle. We have to include all possibilities and integrate over all of them. Okay, so that's a quantum mechanical thing. It's just a reality of quantum mechanics. We have just expressed it in a nice pictorial space-time way, that, well, when a particle goes from here to here, it sort of wanders wherever it feels like, as long as it obeys some probability given by that exponential of Hamiltonian. And then it ends up there, and when I sum over all ways it can end up there, then I get the actual probability amplitude that it did end up there. So nothing wrong with this. And this was sort of Feynman's way of thinking. He was inspired by some conversations he had with Dirac and so on, and Dirac had some early thoughts on this subject, but Feynman really kind of nailed it, I think around 1951 or something, in a very classic paper. And the step that Feynman took is the next step after this, and this is where all the craziness lies. The next step is take the limit of this formula as n goes to infinity. On one hand, it's very appealing because, well, we took all these time intervals, but we just used ordinary quantum mechanics to go from here, here to here, here to here, and then we integrated over some intermediate steps. What if we took these intervals to be as small as they can be in the limit that they are going to 0? Maybe you get something that's even more appealing, because now the integrals, these integrals, embody the fact that the particle can be anywhere when it starts from here and ends. That can be anywhere on the way. That fact is embodied by this, but only at n discrete steps, time steps. But if we take n to infinity, keeping, so t by n goes to very small and n goes very large, such that t by n times n is the total time. We can do that. and or we can try to do that, and we should get a formula. What do we get? Okay. So, does the limit exist? And this is sort of the million-dollar question. There's quite a lot of mathematics research about it, but there's, I think, not yet a very clear conclusion. But we are going to take a practical approach. So from this point on, let's simplify our lives by taking a particular system, a particular class of systems. Up to now, we did say one dimension, but I think you must have noticed that the dimension didn't matter much. If it was three-dimensional particle, I would just put d3x for each of them, and I would put some arrows on the x's, and it would be the same formula, nothing really different. But now I'm really going to take, for the moment, one dimension and a Hamiltonian, which is of standard form that appears in Schrödinger equation in the toy examples that we learn. Because those are toy examples, so we'll work with those for some time, and then we'll go to multi-dimensions and even maybe more complicated Hamiltonians. Okay, good. Now let's calculate this factor. If we understand this factor, of course, then we've understood the result, because we have to multiply it by itself successively many times and do some integrals. So let's try to find a good formula for xb tb, xb minus 1, tb minus 1. But the new thing we'll do, because we are going to take n to infinity, we'll say that tb minus tb minus 1, remember this is equal to capital T by n. All the time steps are in 1 by n of the full time evolution. So we'll call this number epsilon. And we'll work to leading order in epsilon, neglecting terms of epsilon squared and higher. That's how calculus is done. So it's a way to try and do some calculus. As we'll see, it doesn't quite have the same level of success, but that's the idea. Okay. So now let's write our u. So this quantity is equal to xb tb e to the minus I by h bar p hat squared by 2m. I hope I put the hats, yeah, p and x are operators. Okay, this times epsilon minus I by h bar v of x times epsilon. Okay, this is all in the exponent. And then here I have xb minus 1, tb minus 1. All right, all I've done is wherever in the definition of this I had tb minus tb minus 1, I've simply renamed it as epsilon. Nothing else has changed. Okay? Please object wherever you can. You'll learn more by objecting. Any objections? They are both in the exponent and they are added to each other as they should be. Now for the first time I'll use the infinitesimal nature of epsilon to write this as xb tb e to the minus I by h bar p squared by 2m epsilon times e to the minus I by h bar v of x epsilon, and then my original. Okay. Is it correct to go from this to this? How can they commute if one depends on p and the other depends on x? They don't commute. Huh?
Leading order in epsilon.
Very good. So the error in going from here to here is of order epsilon squared. That's the key point. Because you have to take the commutator of the whole exponent with the whole exponent. So you will get this thing, kinetic commutator with potential energy times epsilon, twice epsilon. So that we are neglecting. So here we made an approximation, but we are going to take, so plus this is a standard way to write it, plus terms of order epsilon squared, which we don't care about. Because we are going to take epsilon to 0, we are hoping this will make sense. Good. And now we are in better shape, because now we can insert a complete set of momentum eigenstates between these two exponentials. Yes.
Once we take this approximation, like how do we know that this converges?
We don't. And this is the whole point. We don't know anything about this approximation. We just take the approximation, we land somewhere, we understand that something went wrong on the way, and we say, well, maybe we propose a new way to do quantum physics inspired by this calculation. So as I told you, a door will open in the ground and we'll fall in. We haven't yet fallen in, but you can see some cracks in the ground already because of these extra terms. So there are some things that are disturbing, and they should disturb you, but just keep them in your mind. Now we are going to put momentum eigenstate here, and then we are going to put the other term. Okay, we have a few more minutes to finish this. Okay, now what will happen is that we can also, first of all, this acting on this, p will turn into a number, because this is an eigenstate of p hat and it's going to be integrated. So that we'll keep. Okay. There's also 2 pi h bar, the measure for momentum eigenstates. So this will be dp over 2 pi h bar. Yes, this is fine. Now this will give me the p squared, so I can take this out and put it outside. It's now a number, e to the minus I p squared by 2m epsilon over h bar. Okay. Then I get x with p, okay, which is a e to the ip dot x. This is just the standard plane wave. Overlap of position with momentum eigenstate is e to the ip dot this x. Okay. On this side, I'll evaluate this by acting on that. So v of x hat will become v of xb minus 1. I'll take it out, and then it will be again an overlap of p with this, which will again give me e to the ip dot x, but with the opposite sign. So, collecting everything, I get this, then I get e, yes.
Are we doing like one dimensional or?
Yes, for the moment. The generalization to higher dimensions is quite straightforward for such Hamiltonians. Do you anticipate some problem?
No, I just.
Yeah, I might have to call it d3p and put 2 pi h bar to the 3. So those I'm going to leave to you. There's nothing in this derivation which is very one-dimensional, but just to be very definite, we are sticking to one dimension. Okay, so this is this term, but now x has become xb minus 1. Okay, and then the exponential, which is actually e to the I by h bar p times xb minus xb minus 1. That's all. Sorry for my awful handwriting, but I think this is nothing very difficult. So this one, e to the I by h bar p xb, came from this overlap with this p, and the one involving xb minus 1 came from this overlap with this x, but with the opposite sign, because here p is the bra and x is the ket, here x is the bra and p is the ket, so they're opposite signs. So it's quite satisfying. And note that this has an epsilon, this has an epsilon, that doesn't have any epsilon. All clear? These are literally steps that you could do yourself. If I told you what to do, you could do all of these steps yourself. There is no stroke of genius here. The genius was to try and do this in the first place. Okay. Now we can do the P integral, because for P we have a Gaussian and we have a linear term upstairs, and by completing the square we can do the P integral. It's just a Gaussian. That's clear? Over this and over this. And what can we anticipate? We are certainly going to get this term because it doesn't care about P, it doesn't depend on P. And this plus this will give me something proportional to the square of xb minus 1 upstairs with some coefficient which I need to work out by completing the square. And the answer is u of xb tb xb minus 1 tb minus 1 is equal to square root of m, this is that m, upon 2 pi I h bar epsilon, very important, e to the I by h bar m xb minus 1 squared upon 2 epsilon squared minus v of xb, and all this times epsilon. So let's pause to examine it. This is what I predicted. Because the Gaussian has an epsilon in it, the result will be this thing divided by that. Okay, and actually this is only divided by 1 epsilon, but I took one out, then I put 2 over here. So 1 epsilon extra I put here by hand, but the other one is outside. While this term was always proportional to epsilon, I have done nothing to this term. However, it was v evaluated at xb minus 1. And now I have made it v evaluated at xb. A small change. Again, it's of order epsilon squared. So it's okay. And actually you can, if you want to be more careful, the reason I did that is, you see, this depends on a difference of 2 neighboring x's. So I just want to focus on this one, so I evaluated there, but if I focus on this one, I can evaluate it. At the other, it's just a simple, sometimes these difference operators also, you can take difference with respect to the average point and so on. So there are many ways to do this. But what is noteworthy is we got a definite answer with a definite normalization, and the normalization has both an I and an epsilon in it. Okay.
Sir,
Yes.
aren't xb minus 1 and xb integrated overall?
Yeah, they will be integrated overall. That's
They
okay.
might not be close.
Yeah, it is so there's no, I agree, but here is where actually a little bit of guesswork comes in, because we expect that even though they are integrated over independently, in the limit, when I take this limit and integrate over every point, then I should get back some sort of continuous path, in which case xb and xb minus 1 and xb can't be too far apart. They should be separated by order epsilon. But there's definitely a guess involved there, because in a way we are going to build up a smooth path by these very jagged ones where each point is integrated from minus to plus infinity. So there is this is again one of the aspects of guesswork, though I don't think this is the most important one. But now comes a very brilliant fact, which is that this quantity in the exponent here is equal to e to the IH bar. Now epsilon is a very small interval of time, like dt, and this is a small interval in x. So this is like dx by dt whole squared, or x dot squared. So I have got half m x dot squared minus v of x dt. And something quite miraculous has happened. What? We got the Lagrangian, though we started with the Hamiltonian. Okay. And now we have to take the product of this. Okay, another thing is we got numbers. Now there are no operators of states left. They're all gone. How did they go? The p's were introduced by hand, and then we overlapped them with the x's to get these exponentials. And so after that, p's and x's, all the states are gone. All the operators got evaluated on their respective eigenstates, so they are also no longer operators. So nothing is, so we've got the action, and moreover we've got the classical action. And now we want to multiply together many of these over all different intervals t. And what does that amount to? It's simply the integral of this over t. So therefore, the final answer is u of xn and tn, and x0 and t equals 0. So this one I'm calling capital T, is equal to integral product of root m over 2 pi I h bar epsilon dx multiplied over all x e to the I integral L dt over h bar. Yes.
Initially we have root m by epsilon sitting at the front, and when we take epsilon goes to 0,
Yeah.
then does that not blow up?
We haven't taken it completely to 0 yet. It does blow up. So this is what I'm going to say next, and then I'll stop because we have reached 5 o'clock. So when we examine this answer for the quantity we wanted to evaluate, we find that it's made of two parts. One is gorgeous. It's the exponential of I over h bar times the action integral L dt, which we didn't have from the beginning. It's absolutely lovely. This is very well defined. But the price is that we have to somehow take a product over all x. What does it mean to take a product over all x between x0 and xn? Do you know how to take a product of all values of x between one place and another? You know how to take a sum. That's called Riemann integral. Product, something new. So we are supposed to take a product over all x, and moreover, we have an epsilon sitting here which stubbornly refuses to go away. And these are the two problems. This is one problem, and this is another problem. And we'll stop here, and next time we'll see what we are supposed to do with these problems. We have to find a practical way around them. Okay?